Welcome back, guys. So in this recording, we're gonna continue with our common emitter. Our first example. Last recording we did RO, we did our input, the output resistance and the input resistance, and now with voltage gains. And I'm saying gains because there are three types of voltage gains. Okay, so let's start by the simplest one, the open loop voltage gain. Number one, open loop voltage gain, AV naught. Okay, AV naught is basically the voltage gain when there is no when there is no load. So I'm gonna disconnect the load. Okay, just consider it as open circuit and just solve it. And AV naught is basically equal to VO over V input. Where is V input? The voltage of our input. Where is our input? Between these two terminals, this terminal and the ground. So basically it's between that point and that point. Okay, so let us draw the circuit without considering the load. So RC, beta IB, VO in here, RB, our signal, and here is VI. I forgot RBI. So this is basically RBI, then RB, then our signal V signal. Here is VI. Okay. So AV naught, VO over VI. So let's get VO, let's get VI, and again, whenever you find a characteristic for the amplifier like AV or O or input, the final expression should be as a function of the circuit parameters, like the resistances and the transistor parameters like beta. It's not valid to have IB, for example, or beta IB or IC in your final expression. Okay, let's start by VI. VI is basically the voltage between that point and that point, which is basically the voltage between that point and that point. Okay, remember the current flowing in here is IB. So if we get the voltage across R by, it's basically VI. So VI is basically IB R by. Okay, that's good. How about VO? So look, VO is the voltage across RC between this point and the ground across RC. Look at the flow of beta IB. It's flowing like this. It can't go here because it's open circuit. So it will continue like this. And they come back to that point. So the current is flowing from bottom to up, from the ground to up. So the voltage is opposite. So VO is basically minus the voltage across RC. What is the voltage of RC? Is basically the current times the resistance. The current is beta IB. The resistance is RC. So AV naught equal to IB. I'm sorry, VO over V input. So VO is minus beta IB RC over V input, which is IB R by. IB will go with RB. So this is basically equal to minus beta RC over R by. And that's a valid, expression. Why? It's a function of the circuit parameters and the transistor parameter. RC is known, R by is known, and the beta, of course, is known as well. Okay? That's basically, the open loop voltage gain. Let's take another one, another type, which is basically what's called just the voltage gain. AV, which is VO over VI, but now we're going to consider the load in the circuit. So here you consider load is open. Here load is considered. Okay, that's good. So basically we're gonna have the same circuit, but I will just add the load to it. So it's gonna be like this. R load, RC, exactly the same equivalent circuit, exactly the same. Then R by, RB, R signal, V signal. Here is VO this time. And again, here is VI. So VI will not change. VI is still IB R by. But VO now is going to change because beta IB is now flowing in both resistances. Okay, so VO is basically can be considered as beta IB multiplied over times the parallel equivalent of RC and RL. So VO now is minus beta IB, and then the resistance now is RC parallel RL. So AV is VO minus beta IB RC parallel RL over IB R by. Again, IB will go with IB, so minus beta RC parallel RL over R by. And before we continue, we should stop here for a moment and compare which is bigger, AV naught or AV. Apparently, it's AV naught. AV naught is why? Because RC is greater than RC parallel RL. You know, when we take parallel combination of any two resistors, the resultant will be smaller than the smallest. I mean, if, for example, if you have a resistor like, let's say, how much? 2 and 2, for example, two resistance in parallel, both are 2. So the equivalent resistance will be 1 ohm. Okay, so it's smaller than the smallest. Of course, the smallest here is just both are small because both are equal. But you have this rule all the time that the resultant resistance is smaller than the smallest between the smallest between the combination of resistors that was in parallel. So basically, if RC is the smallest, so the resultant will be smaller than RC. If RL is the smallest, then the resultant will be smaller than RL. So in all cases, RC will be bigger than RC parallel RL. Okay, so that will be bigger than this. So AV here, since RC is greater than RC parallel RL, so AV node will be bigger than or greater than AV. This is all the time, by the way. All the time you're gonna find that AV node is greater than or equal to AV. Okay, or AV equal to AV node when the opposite. AV node is equal to AV when R load tends to infinity. And this is another way to do a AV node. I mean, you can start by AV. Then you can apply this equation to get AV node. Let's try it. So AV is minus beta over R by, because I'm gonna factorize RC parallel RL. So RC parallel RL is basically RC RL over RC plus RL. So divide by RL. So minus beta over R by, and then this will be RL. And here you have 1. We're gonna divide by RL. So this is RC. This is RC. Then RC here over RL plus 1. If RL is tended to infinity, this will be 0. So this will be minus beta RC over R by. Exactly like this one. Okay. So you have 2 ways to get AV node. You can start by AV and get AV node, and you're going to start by AV node just by itself. but remove the load from the circuit. Okay. Whatever you like, go with it. But in all cases, EV naught is greater than EV, and that has a meaning. And this meaning is the load can affect the gain that you get from the circuit. That's basically the meaning, and it's a really important one. The load can affect the gain, the final gain that you get from the circuit. And of course, if the load is zero, let's assume the load is just short circuit, the voltage will be zero all the time, so there will be no gain. Just try it. If RL here is zero, then AV no, I'm sorry, if AV will be, if RL here is zero, AV will be zero. Okay, so the load affects the circuit, the gain that you get basically. Okay, number 3, the overall voltage gain, GV, which is VO over V signal. There are many ways to do that. One, just by looking at the circuit, directly, and another one which I personally prefer is using the equations that I'm gonna drive right now. Okay, so let's do this trick. Let's multiply by VI and divide by VI. So we're gonna multiply by VI and divide by VI. This VI, I mean this guy. Okay, so we're gonna say VO over VI times VI over V signal. Okay, and what is this? This is basically EV, right? This is EV. So GV equal to AV times VI over V signal. We know AV. We just need to get VI over V signal. And to get VI over V signal, there is a very, straightforward way to get it. We said that our input is the resistance seen by these two terminals, right? So I'm gonna remove all, it's equivalent circuit, it's equivalent resistance. So you can just remove all of that and put our input. So let's do that. Let's do that. Here is our input, and then our signal and the V signal. And here is VI. Now we can get, a relation between VI and V signal in a very clear and easy way. So basically these two resistors are in series. So VI equal to V signal, the voltage divider, times our input over our input plus our signal. Divide both sides by V signal. So this will give us VI over V signal equal to our input over our input plus our signal. So GV based on that equal to AV. What's AV? Oh, let's AV, our input over our input plus our signal. Let's get AV. What is AV? AV is minus beta RC RL R by minus beta RC parallel RL over R by times our input divided by our input plus our signal. And remember, we know our input. We know our input. It's let's do it. Let's do it. So minus beta RC parallel RL over R by, and our input is it was RB parallel R by, RB parallel R by over RB parallel R by plus our signal. That's it. That's GV. Let's also stop for a moment. Which is bigger, GV or AV? Just look here. We know already that AV is less than AV naught. Now GV and AV. So our input over our input plus our signal. Put any numbers like a 1 and 2 for our. So if our input is 1 and our signal is 2, so 1 over 1 plus 2, which is this is less than 1, right? Put any number for our input and our signal, you will find that this guy is always less than 1. So basically GV is less than AV. And that tells you that the internal resistance of the source again can affect the gain that you finally get out of the circuit, the overall gain basically. This is the most important gain, by the way, because this is the overall. This is what you can see. AV naught, AV naught is the intrinsic gain. If there is no load connected, if there is no input connected, connected RC, R signal and V signal, this is the gain that you're gonna get. Minus beta RC over R bar. Then once we add the load, it decreased a little bit because it's RC parallel RL right now, not just RC. We connect our signal, it decreased the gain. It decreased the gain. And that gives you an idea that our input is really important. If our input is infinity here, if our input is infinity, if our input is really big, then this guy will be approximately 1, this term. So this will increase JV. Why is that? Basically, just look at here. Look at this circuit. We wish that V signal, all the input goes to the circuit, goes to the amplifier circuit. So we wish that V signal, all of it goes to our input. Also, because of our signal, a portion of it, just a portion of V signal goes to our signal as a voltage drop, and the rest, which is VI, goes to our input. If our input is really big, then V input approximately will be equal to V signal. Or if our signal is small, but you can't control it basically, then also that's good. If it was small, or smaller than, of course, our input, much smaller than our input. Okay, so GV is less than AV and AV is less than AV naught. AV shows you AV shows the effect, let's write it, of our load. GV, the overall, shows the effect of our signal. And implicitly our load, because it's a function of AV. So AV has our load inside. Look, our load here and our signal in here. And from that equation in here, that one, you can say which is bad and which is good for your amplifier. Basically, if RL is really big, if RL is infinity, this is good for it. This will increase GV. If our input is infinity, or this also will increase GV. If our signal is big, this will decrease your GV. If our signal is small, that will increase your GV. And so on. Okay. One final note, guys, that all GV, AV, AV naught are all minus. So all of them in the common emitter case are negative or have minus sign. Okay, and that's also a property for the common emitter amplifier, is that it makes the output amplified but out of phase. Okay, so that means the output, or VO, is out of phase of the input. I mean, if the input is like this, the output is like this. Amplified, but opposite. This is started by positive half cycles and negative half cycles. It's started by negative half cycles and positive half cycle. Okay, and it can be controlled again, like what we said before. It can be controlled using, let's look at AV naught here, beta, RC, and R bar. Okay, another and final note is that recording. We previously deduced the AV as GMRC, if you guys remember, using without using the equivalent circuit model. Okay, we deduced, but using derivative and stuff, we use that AV is GMRC, and it's basically equivalent to that. It's no different. So GM is basically IC over VT. Okay, IC over VT. And basically IC is beta IB over VT. And the beta is, I'm sorry, we can get IB in the numerator, so this will be 1 over VT over IB. And VT over IB is basically R pi. So this is basically beta 1 over R pi. So basically they are equivalent because we said that it was G minus GMRC. So that guy here, beta over R pi, is basically GM. So again, it's equal to minus GMRC. So there is no difference. Actually, this is a very better way to find AV than the one with derivative. This one is long, you know, you need to find a point at which you determine the voltage gain. But here it's really easy. Here it's just a circuit analysis, not derivative or stuff. Okay, guys, that was it for this common emitter circuit. We're going to explore more circuits in the next video. Thank you very much for watching this video, and see you in the next video. Bye-bye.